Welcome back to Educator. The next functional group we're going to take a look at kind of contains two groups. Either the ketone or the aldehyde are going to have very similar reactivity. So let's take a look at both of them. The ketones and aldehydes are molecules that contain a carbonyl. The CO double bond is what we call a carbonyl. And we're going to see that the aldehydes and ketones are the first of many carbonyl-containing functional groups that we're going to be exploring. Now, what's very special about the carbonyl is it has resonance. Anytime we have a pi bond between two different atoms, we know that we can draw a resonance form where we take the pi bond and we move it to the more electronegative atom. And so every carbonyl has a resonance contributor that has an O- and a C+. That, combined with the inductive effects that we have for a carbon bonded to an oxygen, means that overall, every carbonyl has a significant partial minus charge on the oxygen and a significant partial plus on the carbon. That's going to define the reactivity of the carbonyl. For example, what do we associate with something that's partially positive? It's going to be electrophilic. Carbonyls are electrophilic. And what does it mean to be an electrophile? Nucleophiles attack. So nucleophiles add here. And we're going to see again and again and again, example after example of nucleophilic attack onto the carbonyl carbon. Okay, the oxygen is exceptionally partially negative compared to, very electron rich compared to an ordinary oxygen. So that makes it basic. And what does it mean to be a base? It means that you can protonate here. And many of our mechanisms are going to begin with the carbonyl interacting with an acid and getting protonated on the carbonyl oxygen. Okay, those are the reactivities we're going to start with in the next several units in looking at carbonyl chemistry. And eventually we're going to move into some reactivity, not of the carbonyl carbon, but of the next carbon over. This first carbon attached to the carbonyl is described as the alpha carbon. And there's an interesting feature of the alpha carbon is that the protons that are attached to that alpha carbon are acidic. Now, what does it mean to be an acid? It means you donate a proton. So in other words, it can be deprotonated here. And so eventually we're going to start looking at that alpha carbon and deprotonating in that position and seeing what reactions lead from there. So because of this resonance, the carbonyl is a very, very stable functional group, and that's what makes it ubiquitous. We find it all over the place in a wide variety of functional groups. It's extremely strong. It's extremely stable. If we take a look at the bond association energy for a CO single bond, it's 79 kcals per mole, an average of that. So what would we expect for a CO double bond? Typically, if you think about alkenes, we compared a CC single bond, and when we added a pi bond onto the sigma bond, we didn't see a doubling of the bond strength because a pi bond is typically weaker than a sigma bond. And so, what we might predict for the bond strength of a carbonyl, if you were to try and break through the sigma bond and the pi bond, we would expect it to be less than maybe 160. This is about 80. And so if we had two single bonds, two sigma bonds, we would expect it to be 160. So we would expect this to be a little less than this. Well, turns out that the carbonyl strength is 173 kcals per mole. So it's actually stronger to have a CO double bond than to have two separate CO single bonds. So this is extremely unusual. Why is it so stable? It's because it has that resonance energy. It has that resonance energy, resonance stabilization, and so adding that pi bond makes that resonance possible, and so that makes it a very energetically favorable thing and a very, very strong bond. So in fact, what we're going to see a lot of times is formation of the carbonyl can be the driving force of the reaction. That might be something that helps us decide whether or not a reaction is going to be favorable. Anytime we see a mechanistic step that creates a carbonyl as part of that step, we need to recognize that that's a very favorable step. That's a good step to happen. Okay, and like I said, we're going to start with just aldehydes and ketones. So we call it a ketone when the R group on either side of the carbonyl is a carbon. That's called a ketone. And when we have at least one hydrogen attached here, so two hydrogens or one carbon and a hydrogen, that's what we call an aldehyde. And that's where we're going to start with in today's lesson, is looking at carbonyls that have nothing other than carbons or hydrogens attached to the carbonyl. Okay, but there's many other functional groups that contain carbonyls. This, for example, when we have an OH attached to a carbonyl, this is no longer an alcohol. The OH is part of this functional group. Together, the carbonyl and the OH are described as a carboxylic acid functional group. This is a carboxylic acid. When we have an OR group attached to a carbonyl, again, it's no longer an ether. An ether would mean we have an OR attached to just a plain alkyl carbon group. But when it's attached to a carbonyl, we call these esters. When we have a nitrogen here, it's no longer an amine. We call this an amide, and so on. There's a variety of these compounds where attached to the carbonyl, we have some group that has a lone pairs attached to it. Right? Just like the oxygen has lone pairs, nitrogen has lone pairs, halogens have lone pairs. Anytime we have this kind of a structure, these are all going to be related to each other. These are called carboxylic acid derivatives. Of course, this first one is a carboxylic acid. All the others are described as carboxylic acid derivatives. And so after we're done talking about aldehydes and ketones, then we'll move to these other related compounds. So what are some ways that we can synthesize an aldehyde or a ketone? What reactions have we seen that generate CO double bonds, carbonyls? Well, one way we could do it is we could start with an alcohol. So if we take an alcohol and we treat it with an oxidizing agent, we can increase our CO bonds, our number of CO bonds, and decrease our number of CH bonds. That's what our oxidation reactions look like. And so that would be a great way to form a carbonyl. We could get either an aldehyde or a ketone depending on what kind of alcohol we started with, right? We had things like PCC as an oxidizing agent that could do this, or maybe Jones, sodium dichromate, Cr2O7, H2SO4. We had Swern oxidation. Okay, so there are a variety of oxidizing agents we've seen before, and certain situations gave us ketones and others gave us aldehydes as products. Another reaction we saw that's given carbonyl compounds as products is the ozonolysis of alkenes. Ozonolysis means we react an alkene with ozone. It does a lysis. It cleaves the carbon-carbon double bond. And what does it replace the carbon-carbon double bond with? It replaces it with a carbon-oxygen double bond, replaces the carbonyl. So this is a way of making two carbonyl-containing compounds. Again, it can be a combination of either aldehydes or ketones, depending on what kind of alkene we started with here. Remember this DMS, this dimethyl sulfide, is just a reductive workup. The ozonolysis is always a two-step procedure to cleave the bond and form the carbonyls. Okay, and one other reaction we've seen for creating carbonyls was doing hydration of alkynes. You remember that if we add water across a pi bond, we add an H and an OH across one of the pi bonds, and we get an enol, and then that enol will tautomerize to a carbonyl, either a ketone or an aldehyde. We saw that if we were to add with Markovnikov regiochemistry, then the oxygen would go to the inside carbon, and the hydrogen would go to the end carbon. Okay, in other words, we could get a ketone product here. Or if we did hydroboration oxidation, remember that was anti-Markovnikov addition of water, that would give us a product that has the carbonyl on the end carbon. In other words, we could use that to make an aldehyde. So an alkyne might be a possible starting material we could use that we can convert into a ketone or an aldehyde if we wanted to. So what are some of the reactions that we can have for carbonyls? The majority of the reactions we're going to be seeing are going to be reactions with the carbonyl carbon, which is always, always, always partially positive, which makes it electrophile. So we're going to be reaction with a variety of nucleophiles. One such nucleophile is hydride. We've seen lithium aluminum hydride as a source of H-. We can put that in quotes because that hydride is still attached to the aluminum, but it behaves as if it's an H-, so it's convenient to draw it that way. Okay, and what reaction do you expect to have happen when hydride sees a carbonyl? Well, it's going to do the same thing that every nucleophile does. It's going to attack the carbon and then break the pi bond and move those electrons up onto oxygen. So we'll get an O-. and we'll have an H now bonded to the carbonyl carbon, the formerly carbonyl carbon. So that's what we get with hydride. So step 2 here, what's the purpose of step 2? Step 2 is just our reaction workup. We do an acidic workup so that we can protonate anything that needs protonating. And of course, it's the O- here that we want to protonate. So we could just describe HA as coming in and providing a proton. And the product we would get then is an alcohol. So we could take a ketone or an aldehyde and we can convert it to an alcohol by hydride reaction. Now this is described as a reduction reaction. You could describe this as a hydride reduction, because what we did was we decreased the number of CO bonds and we increased the number of CH bonds. That's the exact opposite of an oxidation reaction. So just a little reminder here that if we had a carbonyl, we can convert the carbonyl to an alcohol by a reduction reaction, a reducing agent, something like LAH that we just saw, lithium aluminum hydride. And we also know how to take the alcohol and oxidize it to the carbonyl by using something like PCC. So alcohols and carbonyls are very readily interconverted by functional group interconversions using either an oxidizing agent or a reducing agent. Now, how about a carbon nucleophile, something like some sort of C-? Now, there's two kinds of carbon nucleophiles we can look at. One is just a straight-out carbanion. What carbon can hold a negative charge and just be a salt with something like a sodium cation? Okay, well, there's really only a couple examples of this we've seen. We've seen acetylide anions and we've seen cyanide anions. Okay, and what makes these special and unique and able to hold a negative charge is because they are sp hybridized. That triple bond allows us to simply deprotonate that carbon and use it as a nucleophile. Okay, so for example, if we took acetylene and we react with NaNH2, who is NaNH2? Well, that means we have Na plus, NH2 minus. So NH2 minus looks to me like a very, very strong base. So what happens when a base sees a terminal alkyne or acetylene? This is an acidic proton, and so we're going to deprotonate. Once again, the reason I can deprotonate here is completely because it's an sp hybridized carbon. That's what stabilizes the negative charge. So this is a reasonable nucleophile. And what nucleophile can it react with? Well, that's what we're doing in step 2, is we're reacting with this electrophile. The nucleophile is going to see this electrophile. Again, carbonyl, partial positive, always an electrophile. So what reaction happens? Our nucleophile, in this case our C-, attacks the carbon, breaks the pi bond. Same thing every time when a nucleophile attacks. So we'll end up with an O-, and now we've added a carbon-carbon triple bond here to that carbon. And what do we need to do in step 3? Step 3, we need to have a workup so that we can protonate our O-, and we get another alcohol product. Okay, when a nucleophile attacks a carbonyl, we'll get this alcohol. But this is not a simple reduction reaction like we saw before, because we're actually adding this carbon chain. So what's new here is we've created a new carbon-carbon bond, and that's a really big deal for synthesis. And so what's exciting about carbonyls is they are carbon electrophiles. So if we combine with a carbon nucleophile, we can create an alcohol with a new carbon-carbon bond that's being formed. Okay, cyanide is another example of a carbanion that exists. We could just use that sodium cyanide anion we can have as a commercially available. And once again, it's going to attack the carbonyl and break the pi bond. What's going to happen after workup? We're going to have an OH where we used to have a carbonyl, and now we're going to have a CN attached to the carbon. So in each case, we're seeing we saw hydride attacking the carbonyl. We can also have an acetylide type anion, or we can have a cyanide type anion. Those are all good. These are called cyanohydrins, this structure where you have a CN and an OH on the same carbon. And this is kind of an interesting reaction because this is the only reaction we've seen so far that is reversible. In other words, this can kick back out that molecule of HCN. And so because cyanide is poisonous, this is something that's kind of dangerous. When we have a structure like this, we should know that that's something that could generate some cyanide. Okay, another class of carbon nucleophiles are the organometallic reagents. Now, what's great about organometallic reagents, like a Grignard reagent or an organolithium reagent, remember, all of these are like having an R minus. And what's great about the organometallic is you can have any kind of R minus that you can imagine. So unlike having to have a triple bond for a carbanion, with organometallic you can have phenyl groups, you can have alkyl groups, you can have just about anything you can imagine, all sorts of different carbon chains. So let's look at an example of that. What would happen if I took this aldehyde and I reacted with phenyl magnesium bromide? Well, phenyl magnesium bromide acts like it's a phenyl minus. Great nucleophile. I know my carbonyl is a great electrophile, so let's see if we can predict the product here. I think that nucleophile is going to attack the carbon, break the pi bond. So we now have a phenyl group, a benzene ring. We could draw that out if you want, or you could just keep it a pH, but just to remind what's happening here. We've just added a phenyl ring to this carbonyl carbon, and then after workup, step 2, we're going to end up with an alcohol. So hopefully you're seeing a trend here that reaction of a carbonyl with a nucleophile is going to give some kind of alcohol product. And where this comes in handy is if we are given an alcohol as a target molecule, we can keep that in mind as we plan our synthesis. So if we wanted to take a look at the retrosynthesis of this alcohol, retrosynthesis is asking, what starting materials do I need? What starting materials do I need to make this alcohol? Well, what we just learned was that you can identify that carbon bearing the OH group, and you can take any one of these other carbon groups and do a disconnection there. Okay, now when I do that disconnection, I think about the two carbons that are coming together to form this new carbon-carbon bond, and I ask myself, which of those was a nucleophile, which of those was an electrophile, what did they look like as starting materials so that they could come together and make this product? Okay, well, the R group can be good as a nucleophile. Something like a Grignard reagent would be a great way to make any carbon group nucleophilic, which means this carbon was my electrophile. So what did my electrophile look like? What kind of electrophilic carbon can I have that after a nucleophile attacks it, I'm going to have an alcohol at that position? Of course, it's the carbonyl. So this guy was the carbonyl, so I can draw this ketone, for example, and an appropriate Grignard. A Grignard. So let's check our work. If I had this ketone and I reacted with this Grignard after reaction workup, absolutely I would get this alcohol. That new carbon group would add into the carbonyl, and I would now have an OH at that position. Okay, so this is a very nice strategy to keep in mind. If I want an alcohol, the way I make an alcohol is I work backwards to a ketone and a Grignard. So it's good to keep in mind that a ketone plus a Grignard gives an alcohol. A ketone plus a Grignard gives an alcohol. Ketone plus a Grignard gives an alcohol. It's a great strategy to use anytime you need to do an alcohol synthesis. Okay, let's try and do an example. How about if you were given this transform problem? What are the reagents necessary to convert the given starting material into the desired product? And as usual, more than one step might be necessary. Okay, the way that we need to approach these problems, a systematic approach we should have is we should look at the target molecule, look at this product as a target molecule, and do a retrosynthesis. Ask what starting materials do I need? And when I compare this alcohol to my starting carbon chain, I see that I started with this 6-carbon chain, but now I have this 6-carbon ring plus these extra 3 carbons. That directs me to where I need to do my disconnection. In other words, I know that in the course of this synthesis, I have to form this carbon-carbon bond. So how do I do that? Well, in order to do that, I look at these 2 carbons involved and I ask myself which one was my nucleophile, which one was my electrophile. And I'm going to come back to the carbon that now has the OH. Which part was that carbon? That carbon was the electrophile as a carbonyl. And so this carbon was my nucleophile. How do I make an alcohol? I have an alcohol target molecule. How do I make an alcohol? From a ketone plus a Grignard. Right? I'm really asking what ketone and what Grignard do I need in order to make this alcohol. So I need this 3-carbon carbonyl. I need acetone as my ketone, as my electrophile. And what Grignard do I need? I need this cyclohexyl Grignard. So MgCl in this case, or I can remember I could do a lithium here too. So when I say ketone, what I really mean is ketone or aldehyde, right? Something like a ketone. When I say Grignard, that means Grignard or organolithium would do the same reaction, okay? But ketone plus a Grignard gives an alcohol. It's kind of a nice, simple phrase to remember. Okay, so if I had these 2 components as my electrophile and my nucleophile, they would be able to create the target molecule. That's awesome. So how do I get to where I need to go from where I am? Right now I'm at chlorocyclohexane. Can I go from chlorocyclohexane to cyclohexyl magnesium chloride? Of course, all I need to do is add a magnesium metal, and I can make this Grignard reagent. Once I have my Grignard reagent, I need to add an appropriate electrophile. It's going to be acetone. Was the ketone I need in this case? And I'm on my way to my alcohol. Now, is there anything missing in these reaction conditions? Would this second part work to give me my alcohol? There's something that's missing. I can imagine this Grignard attacking the carbon and breaking the pi bond, but that's going to give me an O-. How do I turn this into an OH? I need to have an aqueous workup. So a Grignard reaction is always going to be a 2-step process. First, we react the Grignard with the electrophile, and then step 2, we add in some H3O+. We do some kind of acidic workup. Okay, it's really important to show these numbers here, step 1 and step 2, to show that these 2 are done in sequence, one after the other. And we can make this alcohol do this transform. Here's another one. What if I had to start with this alcohol and make this, this new alcohol? Now again, I see that I can identify my carbon chain. I have 1, 2, 3 carbons here, 1, 2, 3 carbons. So I clearly see that this is a new carbon-carbon bond that has to be formed in the reaction. Now, if you didn't try and do this with retrosynthesis, you're probably going to fall into a trap. You could say, okay, I need to get rid of that hydrogen and I need to replace this with an ethyl group. So, maybe I can react this with some really strong base like NaNH2. I've deprotonated hydrogens before with NaNH2, and then I can make this anion. And then I can use that as my nucleophile and react it with something like ethyl iodide or bromide and do an SN2. Okay, a lot of times when we just start at our starting material and force our way through to the product, we come up with a problem like that. We make mistakes. Okay, this synthesis would never work as shown. What's the problem here? What's the problem here? First of all, we're reacting with a strong base. Where do I have an acidic proton in this molecule? Do I have any acidic protons? I do. It's up here. This is the only acidic proton, and in fact, this one is not acidic. So even if I didn't have that OH, there is no way I can make this anion. This is completely an unstable anion. And it would be impossible to make it. So we can't just invent new reagents and new reactive species and intermediates that we've never seen before. When have we seen NaNH2 deprotonate a CH? When's the only time we could do this? Only for alkynes. Only if you have a CH on a triple bond, an sp hybridized carbon. That's the only time we're going to do this little trick and deprotonate and then maybe do an SN2. Okay, so this is a failed approach. The reason we fell into this trap is because we didn't do our systematic approach where we look at our product and think, okay, what do I need to make this product? Okay, the retrosynthesis is going to be a better approach. So what starting materials do I need? Now I see the bond that I'm breaking. I see the two carbons involved in the reaction. And I ask, how can they come together? One of them must have been a nucleophile. One of them must have been an electrophile. So which one was my electrophile? The carbon that is now at single bond OH used to be the carbonyl. This was my carbonyl. This was my electrophile. And that tells me that this carbon was my nucleophile. It had to be a nucleophile in order to react with it. Okay, so I see that it's an alcohol. How do I make an alcohol? How do I make an alcohol? I make it from a ketone plus a Grignard. So who's my ketone? I need this 1, 2, 3 carbon with a carbonyl. Look, it's acetone again. I need acetone, and then I need this 2 carbon group to be introduced as a Grignard, MgBr. Okay, or the organolithium would be fine here too. Okay, this is the planning that we need to do. We say if I had acetone and I react with ethyl magnesium bromide, that I could make this product. So now I look back and I see where I start. I'm at isopropyl alcohol. I have isopropyl alcohol. I need acetone. Have I ever seen that synthesis before, that transformation before? Looks like I'm increasing my number of CO bonds. What does that mean? It's an oxidation reaction. Of course, alcohols can be oxidized to ketones or aldehydes. So we need an oxidizing agent. Name an oxidizing agent. We've seen PCC, we've seen Jones, we've seen Swern. Which of these would work? All of them would be good. So just pick one and go for it. PCC is usually my favorite because it's so short and easy to remember. So, and that works in all cases. So PCC is good here. And then what did I want to do with this ketone once I made it? I wanted to react with the Grignard. So once again, a two-step procedure. First, I add in my Grignard reagent, MgBr. Step 2, I do aqueous workup H3O+. Okay, and as usual, any synthesis problem, once you see it solved, it looks so simple. Every step in a synthesis problem should be a simple, ordinary reaction that you've seen 100 times, okay? But it's that combination of reactions and reagents and how you use them and what order you use them that make these multi-step transformations possible. And without a systematic approach, without planning first, we can have some really disastrous consequences. So it's really good to get in a habit of doing this planning at the beginning. Okay, let's take a look at one more example. This one's, again, going from one alcohol to another alcohol. I see we have a 1, 2, 3 carbon chain, and it's not as obvious in this case where those 3 carbons are now. You might think, well, this is 1, 2, 3, but if I did that, now I'd say, okay, here's my disconnection. Somehow on carbon 1, I have to add this ethyl group. So tell me what kind of reactivity carbon 1 has here. How would you get anything to happen with this carbon? Could it be a nucleophile? Could it be an electrophile? Nothing, okay? So there's a problem with this. Let's redraw it and let's think of another way to identify those 3 carbons. And what I'm going to suggest is that carbon 1 started out as a methyl. It's a CH3. It's still going to be a methyl in the product. So where is carbon 1? It's right here. 1, 2, 3. There's my original carbon chain. There's my disconnection. So I have an alcohol. I want to disconnect it and think about my starting materials. I know that one approach is a ketone plus a Grignard. That has worked well for us so far. So I look at these 2 carbons and I think who's going to be my nucleophile, who's going to be my electrophile. And we end up in a bit of a dilemma. This 3 carbon chain, just my alkyl group, can be my Grignard, Okay, this guy was my nucleophile, but what was my electrophile? Could my electrophile be this 2-carbon electrophile? So in other words, the aldehyde? Would these combine to give our target molecule? This carbon would attack, and we would get a 3-carbon with an OH on the wrong carbon. Remember, a disconnection we've seen before was always the alcohol carbon was our carbonyl. Here it's not the alcohol carbon that we're asking to be the electrophile, it's the next carbon over. So this approach isn't going to work in this case with this disconnection. So let's come back and think about what starting materials we really had. Now again, I like the fact that this guy was my nucleophile, but here is the electrophile we need. Let's just look at it as a synthon and say I need something that's electrophilic. I need to imagine an electrophile that's electrophilic not on the same carbon as the oxygen, but the next carbon over. What electrophile have we seen before that the Grignard could be adding to? Well, how about if we kind of add this lone pair back in, what electrophile would you end up with? How about an epoxide? Have we ever seen an epoxide as an electrophile, an epoxide being an electrophile? Of course. Okay, so ketone plus a Grignard is not the only way to make alcohols. It's just going to be the most common way we're going to see repeated throughout. But of course, you can maybe have a disconnection at the next carbon over, and you could do an epoxide ring opening to give that pattern. Okay, so if I had this Grignard and this epoxide, yes, they would combine to give the target molecule we're shooting for. So now I look back at where I am. I'm at an alcohol, and I need to turn this into a Grignard. So where do Grignards come from? Let's keep doing our retrosynthesis. How would you make propyl magnesium bromide? Well, I would need a bromine in that position. I would need a halide of some kind in that position, and then I can convert it to the Grignard. So what I'm going to need to do first is convert this to a bromide or a chloride or an iodide, your choice. What would be a good reagent to do that? Maybe PBr3 would be a good choice. There's no chance of rearranging. Remember, that makes the good leaving group, and it displaces it with the bromine. Okay, so now we have our alcohol halide. What did we want to do with that? We wanted to make that the Grignard reagent. So we just add in some magnesium metal. And now we have the Grignard. That's our nucleophile. What do we do with that nucleophile? What electrophile do we need? We wanted this epoxide. This is called ethylene oxide. So this will bring us to our target molecule by reacting with ethylene oxide. And as usual with our Grignard, it's going to be 2 steps. First, step 1 is react with the epoxide. Step 2 is do H3O plus workup. Okay, so synthesis of alcohols requires identifying the disconnection and then looking at the 2 carbons involved, saying who would be a nucleophile, who would be a good electrophile. And as always, we want to work back to starting materials and reagents that are recognizable, that are simple, that are things we've seen before, we've used before, so we know the synthesis is going to work once we put it all together. Okay, here's one more. I'm starting out with the phenyl and this carbonyl. I still have the phenyl and this carbon. So now I have 2 carbon groups that I need to add in. This is going to be a little more challenging. Well, we can start with either one of them. Let's start with this disconnection here. So these are the 2 carbons that we want to come together. This is an alcohol, so let's try and go back to a ketone plus a Grignard. And the carbon that now has the OH was my carbonyl, so I need this ketone. And my Grignard in this case is a 3-carbon chain. There's my electrophile, there's my nucleophile. So I need to have this ketone and this Grignard if I want to make the target molecule. So that's good. But now I compare my aldehyde and my ketone and say, okay, how do I get from an aldehyde to a ketone? Can I deprotonate this CH with a strong base and add in that alkyl group? Can I deprotonate here? No, what we keep, and when we're trying to take that approach, again, we're grasping at things because we don't know how to get there, okay? We have to think about the reactivity of this carbon. Carbon 2 is a carbonyl carbon. It's an electrophile. So how are we going to add in this isopropyl group? We're going to add it as a nucleophile. So let me show, this is a nice example because after working backwards a little bit, maybe we get stuck. So let's go ahead and start working forwards a little bit and see if we could bridge the gap in between. Okay, if I wanted to add this isopropyl group, how do I make it nucleophilic? I just add on a metal, magnesium bromide or lithium. So step 1, magnesium bromide. Step 2, H3O plus. I would be able to add one of my carbon groups. So this clearly is moving me towards my target molecule. The question is, how do I add the second carbon group? Can I just add in my second Grignard? Is that going to add in the second one? Do alcohols react with Grignards? Well, in fact, they do. They don't do it to form a carbon-carbon bond. This simply acts as an acid, and the Grignard acts as a strong base, and in fact, you would just deprotonate. That's not what we want to do, okay? So this is where our planning came in. When can we use this propyl Grignard? When we have a carbonyl to react it with. We don't have a carbonyl. We need a carbonyl. If I had this carbonyl, now I see where I can go with it. I can add in my Grignard. So how do I go from an alcohol to a carbonyl? This is an oxidation. All we need is PCC, and we can get to our carbonyl, and now we're ready to add in our second equivalent of the Grignard, or our second type of Grignard, H3O plus, and it works. So in this case, because I had to add 2 carbon nucleophiles to my carbonyl carbon, what I did, the strategy was to add the first carbon nucleophile, okay, to give me an alcohol product, and then I had to reoxidize to a new carbonyl so that I could add a second equivalent of the Grignard, a second nucleophile, to add the second carbon group. So I like this example because sometimes when you're doing your retrosynthesis, if you get stuck, just try working forwards a little bit, and when we go in both directions, hopefully that will get us through the entire synthesis. Now, another interesting reaction we can have for carbonyls is a very special kind of nucleophile called a Wittig reagent. And this undergoes what's known as a Wittig reaction. Notice it's spelled with a W, but it's pronounced with a V. It's a German word, German name. And a Wittig reagent is an example, as a typo, of a resonance stabilized carbanion. So it looks like this. It's got a P plus attached to a C minus. So this is called an ylid. An ylid means that you have a plus and a minus charge in the same structure. It's called a phosphonium ylid because that's what we call a P plus, phosphonium ylid. And this has resonance stabilization. So there's a second resonance form we could draw for this, and that's taking this lone pair and bringing it in as a pi bond. And this is another way that we can draw it. So the Wittig reagent is something we can draw either way. We should get used to seeing either way. Sometimes it's just drawn as a phosphorus carbon double bond, and sometimes it's drawn with a P plus and a C minus. Doesn't matter which way we draw it, it's the same thing. We're going to see what it does. Okay, but this is resonance stabilized, which is why it's okay to have this C minus. Ordinarily, we don't want to have a negative charge on a carbon, but this is a possibility. This one's okay. What are we going to do with it? Well, when we see a Wittig reagent like this and we react with either a ketone or an aldehyde, what we're going to do is we're going to identify the carbon group that's attached to the phosphorus, and we're going to replace the oxygen of the carbonyl with that carbon group. So where we used to have a CO double bond, we're now going to have a CC double bond. Here it was a CH2, so now it's going to be a CH2. So the Wittig reaction turns a ketone or an aldehyde into an alkene. So this is an excellent method for synthesizing alkenes from carbonyls and aldehydes. I'm sorry, for ketones and aldehydes. Let's take a brief look at the mechanism. The mechanism is a little strange compared to some that we've seen before, but I do want you to see how, so it's not just magical where this carbon-carbon double bond comes from. Okay, and the reaction starts out simple enough because when we look at this resonance form of the Wittig reagent and we see the C minus, we see how it's clearly a nucleophile. We have a C minus. Our carbonyl we know is an electrophile, so what's going to happen first? Same thing that always happens. Our nucleophile attacks the carbonyl, breaks the pi bond. Okay, this now gives us an O minus, and attached we have this, the carbon group plus this triphenyl phosphine group. Okay, now because we have a P plus and an O minus that are kind of close to each other, what happens is the oxygen then bonds to the phosphorus to make this four-membered ring. It's called an oxaphosphatane. So we get this oxaphosphatane intermediate. Very rare to see a four-membered ring, I know that, but phosphorus on the periodic table is below nitrogen. Phosphorus is bigger, so it kind of has bigger arms. That four-membered ring is not nearly as strained as we would associate with, a carbon or an oxygen type ring. And then this is not our final product. This falls apart. This falls apart by undergoing a pericyclic reaction. What happens is this bond breaks and becomes a pi bond, and this bond breaks and becomes a pi bond. So these 4 electrons and these 2 arrows all rearrange at once. What we form then is this is where we get our pi bond for a carbon-carbon double bond. And what else is formed in this reaction? We get a phosphorus with 3 phenyl groups on it and a PO double bond. So we get this triphenylphosphine oxide as a byproduct of our Wittig. This is something that we can separate, we can filter off, and we're left with an alkene product. So where does the Wittig reagent come from? It's going to be 2 steps to prepare this, and it comes from an alkyl halide. So for example, if we wanted to make, let's redraw the Wittig reagent we just used on the previous slide. If I wanted to make this Wittig reagent, which has just 1 carbon on it, the way I would start is I would start with the 1 carbon alkyl halide. Okay, obviously I need to introduce this triphenylphosphino group, and so that's what I use. This is called triphenylphosphine. Triphenylphosphine, awesome nucleophile. Again, phosphorus is right underneath nitrogen. We know nitrogen is a very good nucleophile, loves to do the SN2. Phosphorus, because it's even bigger, more polarizable, excellent, excellent nucleophile. So when it sees an alkyl halide, very readily we'll do an SN2 mechanism, backside attack, and form this carbon-phosphorus bond. Phosphorus now has 4 bonds, so we count 1, 2, 3, 4. And just like nitrogen, phosphorus wants 5, so it's missing an electron. That's why we have a P+. Okay, so that's our first part, and we can, let me draw this in the other resonance form also, so we can kind of think about, it's always nice to consider where we're heading when we're considering a mechanism or a synthesis on how to get there. So we've introduced this P plus part. What we now need is the C minus part. We started with a CH3, and now we want it to be a CH2. So what's happened here? Looks like we've done a deprotonation. We need to deprotonate, so the reagent we need for that is a very strong base. The base that we typically use in the Wittig reagent is butyllithium. Extremely strong base. Where have we seen butyllithium before, or any organic lithium? We've seen it as an organometallic reagent, just like a Grignard. This would be an incredibly strong base. It's just like any organolithium we've seen, or like a Grignard reagent. This one is just pretty available, commercially available, and so it's an excellent strong base to use anytime we need it. So what we're going to do is we're going to grab one of these protons. Let's just make this a CH2, and so we can see one of these protons and our butyl minus that we have. Of course, we're going to put that in quotes because it's not really butyl minus. It still has the metal attached, but it acts like butyl minus as a base. It's going to grab that proton and either put those electrons right on the carbon, so we have a P plus C minus, or you could draw the other resonance form where it brings the 2 electrons in as a pi bond. Either way, we now have the Wittig reagent, and we got there in 2 steps. SN2 with triphenylphosphine, and then strong base to deprotonate that carbon. Okay, let's try to predict the product for a Wittig reaction. We're starting with an aldehyde or a ketone. This is the substrate for a Wittig reaction. Here's our Wittig reagent. I see we have a P plus and a C minus. And how do we predict the product of a Wittig? Very, very simple. I know the mechanism is a little scary, but predicting the product is very simple. We find the carbon group of the Wittig reagent. It's whatever group is attached to the phosphorus, and we replace the oxygen and the carbonyl with that group. So we replace our CO double bond with a CC double bond. And what did this have? This had 3 carbons. We're going to add 3 carbons. That's kind of a nice way that you can check to make sure you've done the Wittig reaction. This started with 3 carbons. We're adding a 3-carbon aldehyde and a 3-carbon Wittig. We need to have a 6-carbon product. That's a good way to make sure you haven't lost any carbons. Maybe if you're doing a line drawing, you might come up with that a little bit. So we're going to get an alkene product. The Wittig reaction is a great way to make alkenes. So knowing that, if we ever have an alkene as a target molecule, one way we can make this is by doing a Wittig reaction. So the Wittig disconnection is completely breaking through the carbon-carbon double bond, because in the Wittig reaction, both of those 2 bonds are formed during the course of the mechanism. So what we'll do is we'll completely cleave it, and one of these carbons was the nucleophile, one was the electrophile, and because it's an alkene, you can pick either one. Typically the one that is a little less hindered would be the better electrophile. So we could put the carbonyl in the less hindered position. In other words, an aldehyde would be better than a ketone for the Wittig, a little faster, but both would be okay. Which means this guy was my nucleophile. And how do you make it a nucleophile? It's going to be a Wittig reagent. So one possible disconnection for an alkene is to work backwards to a suitable Wittig reagent. What does this Wittig reagent look like? It's a 6-membered ring with the PPH3 attached with a double bond. Or you could draw the C minus P plus, same thing. So this is our Wittig reagent. That's our nucleophile. And what is the electrophile? We had this 2-carbon carbonyl. So that's just an aldehyde. It's acid aldehyde. Now, typically when we draw aldehydes, we usually draw in that CH in the line drawing. It's acceptable to leave it off, but convention usually puts it in there. So we'll add that in there for clarity. And so in this case, it's an aldehyde. That's going to be our electrophile. Okay, so let's see if this is the Wittig reagent we need. Let's see if we could do a synthesis of this. You may be given instructions where you could just use a Wittig reagent and assume it's commercially available. But if you had instructions, let's say you had instructions where the starting materials had to be alcohol starting materials only. For example, that makes the problem a little more challenging. So in other words, now you have to make this Wittig reagent starting from an alcohol. You have to make this aldehyde starting from an alcohol. And so let's think then about this Wittig reagent. Where do Wittig reagents come from? We saw that it's a 2-step synthesis, and it comes from an alkyl halide in that position. So we need a halogen in that position. Chloride, bromide, iodide, your choice, whichever one you want. Okay, so I need cyclohexyl bromide, but I have to start with cyclohexyl alcohol. How could I convert that to the bromide? Well, there's a variety of reagents. I could use PBr3, or in this case, because there's no possible rearrangements to give any other product, I could maybe use something like HBr. That would work well to give this bromide, so a few possibilities here. Those would both be good. And then how do I go from the bromide to the Wittig reagent? How do I get this double bond PPH3? Remember, there's going to be 2 steps. The first step, and we could do them both over one arrow. The first step would be to introduce the phosphorus as triphenylphosphine. Triphenylphosphine, great nucleophile, so that does the SN2. And then the second step is to add a strong base, something like butyllithium, to do a deprotonation. So those are two-step procedure to make the Wittig. And then we want to add this aldehyde. Where does the aldehyde come from? If we had to have an alcohol starting material, we could start with the 2-carbon alcohol, ethanol. And how could I go from an alcohol to an aldehyde? That looks like an oxidation reaction. I know how to do that. We have PCC and Swern and Jones. Are all three of those okay here? Well, remember, because this is a primary alcohol, this is the case where if we use something like Jones conditions, sodium dichromate and acid, chromic acid oxidation, this would over-oxidize and give me the acid. So in fact, I want to use either PCC or Swern to do this. So now I have my aldehyde, now I have my Wittig reagent, I mix those together, and I have my target molecule. So now that we know about the Wittig reaction, this is going to be one additional way that we can do a disconnection for a target molecule, and it turns out that this synthesis is often much more reliable than forming an alkene by dehydration or by elimination reaction. So the Wittig reaction is very widely used in the synthesis of alkenes. Now, everything we've seen up to now for reactions with aldehydes and ketones have been carbon nucleophile. Well, we saw the hydride nucleophile, but we also saw carbon nucleophiles, the acetylide or cyanide or a Grignard or the Wittig, okay, forming new carbon-carbon bonds. We're going to shift gears now and take a look at reactions with oxygen nucleophiles. And what's interesting about oxygen nucleophiles is right here, we see that this is reversible. Okay, the other reactions we saw, I know the cyanohydrin was one exception for that, but hydride and Grignard and Wittig, these are all reactions. Once you form a carbon-carbon bond, you don't go back from there. You don't break that carbon-carbon bond. But the oxygen nucleophiles are going to be something that you can form the CO bond, and it's going to be possible to break that CO bond. So the first oxygen nucleophile we'll consider is addition of water. Okay, when we do that, the product we get is called a hydrate. Now, as usual, this carbonyl is going to be my electrophile. If water was my nucleophile, if we just think about the pattern we've seen up till now, what does it look like? What does the product look like after a nucleophile attacks the carbonyl? We know that we end up with an OH where the carbonyl used to be, and if water was my nucleophile, what do we end up with here? We end up with another OH. So what we've done is we've added water to the carbonyl. The oxygen is a nucleophile, and then we protonate the original oxygen, and this structure is called a hydrate. It's called the hydrate of an aldehyde or a ketone because we've literally added water to it. Now it turns out that this is a pretty unstable arrangement of functional groups. A carbon does not want to have two separate CO bonds and two OHs attached to it. This is extremely unstable, and so in fact, because it is reversible, it turns out that the reverse reaction is favored. Anytime you have this arrangement, it would rather rearrange and do a mechanism to get back to the carbonyl. This is more stable as the carbonyl. Can you think of why that is, that we would want to have this carbonyl instead of the two separate CO bonds? Remember, we started talking about how stable the carbonyl functional group is, how energetically favorable it is. This has resonance. So we don't want to give that up to form this product. So although ketones and aldehydes can react with water as a nucleophile, it's not a very rarely a favorable reaction, so I'm not going to spend much time about it. There are a few exceptions, though, where the hydrate is in fact formed to a significant amount. Okay, one such example of that is formaldehyde. So the very unique example of an aldehyde is when we have two hydrogens attached to the carbonyl. That's called formaldehyde. And it turns out that this is very reactive. It's extremely reactive. We have just these hydrogens here, so compared to a ketone that has carbon groups alkyl groups that can donate electron density, this is a great electrophile. It's very reactive. It's a huge partial plus. It has no steric crowding of any kind because we have just hydrogens here. So that makes it really susceptible to nucleophilic attack. And so if you put it in a solution, like if in a water solution where water is around, water will attack it. And it turns out that in an aqueous solution, you have, the vast majority, 99% of the structure looks like this instead of the carbonyl. Okay, because this carbonyl is really quite reactive. Okay, but any other aldehyde and any other ketone, we have the opposite. It would prefer to be the carbonyl. Okay, another interesting example is that the hydrate is going to be favored when you have a significant partial positive right next to the carbonyl. So this is an interesting molecule. It's known as chloral. And we know that the carbonyl carbon is partial positive, has a significant partial positive because of the resonance contributor that puts a positive charge on the carbon. Okay, now if on the alpha carbon, meaning the next carbon over, I put 3 chlorines, well, I know each of those chlorines is electronegative, and those chlorines pull electron density away from this carbon. It turns out that this alpha carbon is also significantly partial positive. Well, this is going to be something that destabilizes this molecule. The adjacent partial positive destabilize the molecule. And so what's going to happen is when you put this in water, we're now going to get formation of the hydrate. So instead of a carbonyl, we have 2 OH groups. And this now is going to be favored in the forward direction because you have less of a partial positive when you have the 2 separate OHs. So this carbon is now less of a partial positive, so we don't have those extremely electron deficient carbons right next to each other. So this would be something that in this rare case, rather than have the carbonyl, we would rather have 2 separate OH groups. Okay, this molecule is called chloral hydrate. It's something that can be isolated because it's reasonably stable. And this has an interesting history. If you've ever heard of Mickey Finn knockout drops or watched an old movie where they suggest that they slipped him a Mickey, this is the molecule that's used for that chloral hydrate. It can give off chloroform, which acts as an anesthetic. And so this is something that that can be used to render a person unconscious. So chloral hydrate is an example of one of those unique molecules where we would prefer to have the OHs. Now the other oxygen nucleophile we're going to consider is if we have an alcohol reacting with a carbonyl. And now this is a reaction that can be driven in the forward direction and can be quite useful. When we react an alcohol with a carbonyl, a ketone or an aldehyde, the product we're going to get is known as an acetal. So let's take a look at this reaction. If we take a ketone, this is our electrophile, we react with an alcohol as a nucleophile. There's our alcohol. In the presence of TSOH, this is tosic acid. So you could just say HA here. It doesn't have to be tosic acid, but you do need an acid catalyst. And tosic acid is a nice choice. That stands for toluene sulfonic acid. It looks a little like tosyl chloride, the reagent we've used before. So if we have the tosyl with an OH group here, this is extremely acidic. In fact, this structure looks a lot like sulfuric acid. Sulfuric acid has these 2 SO double bonds and has an OH here and another OH here. So we know sulfuric acid is a very strong acid. For the same reason, tosic acid is a very strong acid. But by adding in this aromatic ring, it makes it soluble in organic solvents. It makes it more nonpolar, and so this is a nice acid to use when we're using organic solvents. So what happens? Let's imagine what can happen. What product would you get if alcohol was your nucleophile? Well, we would end up adding an OR group to the carbonyl carbon, and where we used to have a carbonyl, we would get an OH. So this structure is in fact what's formed. However, this is just an intermediate structure. The reaction doesn't stop here because a second equivalent of alcohol is going to come in and react. And what will happen is we'll end up replacing the carbonyl oxygen with 2 separate CO bonds, both of them being OR groups. And when you have one carbon with two OR groups attached, it's no longer called an ether. An ether would be if we just had one OR group. But this one carbon with two OR groups is described as an acetal. Its functional group is called an acetal. Now, and for that reason, this structure here, where you're kind of halfway towards the acetal, is called a hemiacetal. Just like a hemisphere is half of the globe. So because you have just one OR group, we call this a hemiacetal. This will continue. This is not stable. It will continue until we get the full acetal. Now, we just talked about for the hydrate how we would rather have a carbonyl than two separate CO bonds. And why is it possible in this case to get the two separate CO bonds? Well, you're right. It's not something that's going to happen spontaneously and just on its own. The other product in this reaction, what's missing here? Well, we lost this oxygen. Plus, we have the hydrogen from this alcohol and the hydrogen from this alcohol. The other product is going to be water that's formed in this reaction. So the way we push this acetal formation reaction forward is we have to remove the water as it's formed. Must be removed to push the equilibrium forward. And that's because every step along this mechanism is reversible. Every step we do can be undone. And so the only way to push it in one direction or the other is we have to, by removing one of the products as it's formed, Le Chatelier's principle, we're just going to keep going forward to replace that. And if water's not here, we can't do the reverse reaction. So it stops the reverse reaction and promotes the forward reaction. So first, let's take a look at an example of this reaction, see if we can predict the product, and then we'll explore the mechanism. So what if we took this aldehyde and we reacted it with methanol and tosic acid? Methanol and tosic acid. Well, what's going to happen is we're going to replace our CO double bond with two separate CO bonds. And the group that's going to be added is whatever OR group we have in our alcohol. So because it's methanol, we're going to add a methoxy group on one side and a methoxy group on the other side. Okay, so we're going to go from an aldehyde to an acetal. Now, we can always assume that we have an excess of a reagents. In fact, in this reaction, what you would do is you would use the alcohol typically as the solvent. So you have a huge excess of that nucleophile. And so we assume that we're going to be able to go completely to the acetal because we have enough equivalents. We need the two equivalents. We'll have them both here. Okay, of course, our other product is water. If you want to balance your reaction and have everything there, although typically a lot of times predict the product, we're just looking for the organic product. What is the fate of this organic starting material? Okay, so let's use this example and let's think about the mechanism. How is it that we go from this aldehyde to this acetal? Now, let's think a little bit about the mechanism before we get started with it. I notice that they are acidic conditions because I see tosic acid. In fact, this is always going to be true. Acetal formation always requires an acid. So what do you think the first step is going to be? If you see there's an acid present, what do acids do? They donate a proton. They're going to protonate something. So first step is protonate, always. When you have an acid around, strong acid around, you're going to find something to protonate. That's what's going to get the reaction going. Okay, now another thing to keep in mind we've seen acid catalyzed or acidic condition mechanisms in the past, and what was always true was for the charges in that reaction, all of our species are going to be either neutral or they're going to have a plus charge. We're not going to have any strongly basic species like hydroxide or alkoxide. We can't have either of those in acidic conditions. So we'll keep that in mind too when we're doing our mechanism. Let's take a look at that. So the mechanism for acetal formation is going to start, because we have our acid, is going to start with a protonation step. Where can we protonate? Well, we have a couple oxygens here. We can protonate the alcohol, and that will happen. But the protonation that's going to get our mechanism started is instead when we protonate the carbonyl oxygen. So we'll do that instead. Remember, our mechanism, we want to move us in the forward direction. So we're going to protonate in the place that we need to. and that's up here. Now, every step of this mechanism is going to be reversible, so we want to make sure that we draw this as an equilibrium as we go from one step to the next. So protonate the carbonyl. Now, what does that do for us? Why is that a good first step? Well, we know that a carbonyl, what kind of reactivity does a carbonyl have? Is it acid, base, electrophile, nucleophile? It's an electrophile. Every carbonyl is electrophile because it's partially positive on the carbonyl carbon. Well, what do you think is going to happen once we protonate that carbonyl? Now this carbonyl is positively charged. Is that good for being an electrophile? Sure, an electrophile is supposed to be electron deficient. This is even more electron deficient now. It's actually got a positive charge. So this is a great electrophile. When we see a species like this, we want to think about looking around for a nucleophile and having it attack. So what nucleophile do we have? Our reaction is done in methanol. We have methanol as our solvent, and that is most certainly going to be our nucleophile. What happens when a nucleophile sees a carbonyl? It attacks the carbonyl, breaks the pi bond. So this top oxygen now is back to being a neutral oxygen. 2 bonds, 2 lone pairs. Tell me about this oxygen. What does that have attached to it? Still has the CH3 and the hydrogen. Does it have any lone pairs? It used to have 2, but these 2 electrons are now in this bond being shared as a bond, so it just has 1 lone pair left, and this now looks like it's not a neutral oxygen, is it? Let's check. 1, 2, 3, 4, 5. Oxygen has 5, but it wants 6, so this is missing an electron. It's positively charged. And so I know my mechanism isn't done here. I need to get rid of that positive charge. How can I do that? Well, I can get rid of this proton because I need to have only 2 bonds to oxygen. So if I get rid of this proton, what I can use is I can use my A- that I formed in my first step to come grab that proton, or I can use my methanol to come in and grab that proton. Both of those are reasonable. Methanol is probably the better choice since that's our solvent. We have more of that, but this has some nice bookkeeping. So we can attack the proton and leave the electrons on the oxygen. So let's take a look at what we've accomplished so far. What mechanism did we have? We protonate, and then we attack, and then we deprotonate. Protonate, attack, deprotonate. Have we seen that pattern before? Absolutely. This is a very common pattern that we have for acid catalyzed reactions. Okay, and have we gotten closer to our product? We have. We know that eventually we got rid of the carbonyl, and we know eventually we have to get 2 methoxy groups here, and we've installed one of them. We have an OCH3 and we have an OH on the same carbon. What functional group have we just converted the aldehyde into? When we have an OR and an OH, we call this a hemiacetal. So you know you're going in the right direction in acetal formation, right? This is an acetal when the first thing you should be doing is making the hemiacetal. Now we need to, again, thinking about where we're going, we need to get rid of this OH and replace it with an OCH3. That's where we're headed. How can we do it? What can we do to move that substitution in the right direction? How about if we protonate the OH as our next step? Not a bad idea too, because remember we're in acidic conditions, so if you're stuck somewhere, we have a neutral compound. Let's find a place to protonate to get us going again. Now what does that do for us? Why would that maybe move us in a forward direction? Well, by protonating the OH, it gives us a very good leaving group. We turn this into a great leaving group, so if we want to do a substitution and get rid of that group, this would be ideal for that. Okay, now here's the question. How does this leaving group leave? We've seen substitution mechanisms before, right? We've seen SN2 mechanisms, backside attack, where a nucleophile comes in and a single step kicks out a leaving group. We've seen SN1 mechanisms, where a leaving group just leaves on its own, and then a nucleophile comes in. Okay? Neither of those mechanisms are for tetrahedral carbons bearing a leaving group like an alkyl halide. neither of those examples are going to accurately describe carbonyl chemistry, which is what we're dealing with in this unit. Instead, the way we're going to describe this substitution is this intermediate is called a CTI. That stands for a charged tetrahedral intermediate, and we're going to look more closely into that definition in the next slide. Okay, but what we have essentially is on the same carbon we have a leaving group, and we have a group that can help push that leaving group out. And so what happens with CTIs is they collapse. And the collapse of a CTI looks like this. The leaving group leaves, but it doesn't just leave on its own. It leaves with the assistance of that second group. So we use these two arrows to help push the leaving group out, and let's see where that brings us. When we follow those electrons around, we end up with this structure. Now, and what did we just kick out? We just kicked out our molecule of water. We know that we form water in this product. We know that that water must be removed in order to push the equilibrium forward. So this is the point at which the water is removed and the reverse reaction can no longer happen. Okay, now let's take a look at this structure. Something's missing on this structure. I had a positive charge and I lost a neutral molecule. There still must be a positive charge somewhere. Where is it? Yeah, this oxygen has 1, 2, 3, 4, 5. Oxygen 1, 6. So this is an O+. Okay, so still we're moving in the right direction. We've gotten rid of that oxygen that we needed to replace that OH group. Where do we go from here? What does this structure look like? Do you think it's going to be a good nucleophile, electrophile? It's got a positive charge. It's got a carbonyl with a positive charge. Have we ever seen a species like that? Yeah, right here. Right here. What did we say about this type of carbonyl with a positive charge? It's a great electrophile. It's a great electrophile. So what do we do next? We look around for our nucleophile. This is how our second equivalent of the alcohol comes back in as our nucleophile. And what mechanism can you imagine happening? It attacks the carbon, breaks the pi bond. So now we have, at this bottom carbon, we're back to just a nice neutral methoxy group, OCH3. What do we have on this top carbon? Because methanol is what it attacked, we have a hydrogen, and we have a methyl is still there, one lone pair, and positive charge. How close are we to our acetal product that we have? How close are we? We just have one proton left that we need to get rid of, and that will give us our acetal and get rid of our positive charge. So our final step in this mechanism is going to be deprotonation. So again, I can use my A- to come in and deprotonate. And look what we made. We converted the carbonyl, the CO double bond, into two methoxy groups. So remember what we pointed out, what we just thought about on the previous slide. We said our first step is going to be protonate because we're an acid. We said all of our species should have positive charges or should be neutral. Take a look. There were no negative charges here. Okay. It might be tempting sometimes to use methoxide as our nucleophile. Okay, that would be a quick way to put in a methoxy group, but there is no methoxide in strongly acidic conditions. So instead, methanol is the nucleophile we have to use. Okay, so note the charges, no HO minus or RO minus. And the other thing to note is that it is catalytic. It is catalytic in acid. That means for every step where I use an acid and protonate, there is another step somewhere where I deprotonate and get that acid back. So I used HA here, and then I reformed HA. And then here's another step. I used HA here, I protonated, but then at the end, I deprotonated and got that HA back. So to form an acetal, you take an aldehyde or a ketone, dissolve it in an alcohol with just a trace amount of acid, just a catalytic amount of acid, and we will form this acetal. So let's take a little closer look at what describes a CTI, because we're going to see these mechanisms again and again when we're looking at carbonyl mechanisms. What does it mean to be a charged tetrahedral intermediate? Well, the first thing that we're going to start with is something called a tetrahedral intermediate. Tetrahedral means that we have an sp3 hybridized carbon, so that means there's just 4 single bonds to that carbon. And at least 2 of those groups have lone pairs. So we have a situation like this, where attached to a carbon we have 2 separate groups that have lone pairs, at least 2. Turns out that this arrangement can be unstable. This is inherently unstable. We saw it when you have an OH and an OH. That structure is not so good. When you have an OR and an OR, that structure is something that can react and can be undone. Okay, and the way it becomes unstable is when it becomes a charged tetrahedral intermediate. So this is what CTI stands for. And it's when you have this same situation, tetrahedral carbon with 2 groups as lone pairs, but now one of the group has a charge. Okay, and when you have this, then you get an intermediate, you get a structure that can collapse. Okay, now we're going to encounter CTIs in acidic conditions and in basic conditions. Of course, in this unit, acetal formation is always acidic, so we're going to get something like this. We're going to get a CTI where we have one group with lone pairs and another group with a positive charge. So what we just did, let's say, is protonate with our acid. That makes this a very good leaving group. And so what happens is that leaving group will leave. Collapse of a CTI means the leaving group leaves, but it does so with assistance from that lone pair. So it can collapse. We have 2 arrows, and we describe this as kind of a push-pull relationship going on. The leaving group is pulling as usual and doing its leaving group thing, but you have someone pushing them out at the same time. This makes it a very favorable reaction. Okay, in a base catalyzed situation, our CTI is going to have a negative charge, and now that's going to make the group that's doing the pushing real good, and that makes the other group our leaving group. And so same 2 arrows. In this case, the group with the negative charge does the pushing, and the neutral group is what gets kicked out. Okay, so 2 arrows to collapse a CTI, and then we go from there. Okay, now the key is when you see a CTI, when you see a charged tetrahedral intermediate, by recognizing that as such, it's going to help guide you in your mechanism, because you know what a possible thing that it can do is it could collapse and kick out one of the groups and go from there. So let's summarize what we've seen for acetals. If we take a carbonyl and we treat it with an alcohol and some acid, like lactosic acid, we replace that carbonyl with 2 OR groups. In other words, it adds 2 equivalents of ROH, 2 equivalents of the alcohol. Okay, it turns out that if you take an acetal and you treat it with water, H3O+, so if you treat it with water and acid, the reverse reaction can take place. And we can go from an acetal, so we can have a ketone or an aldehyde here, and we go to an acetal. If we have an acetal and we treat it with water and acid, it can go back to the carbonyl and kick out your molecules of alcohol. Okay? Now, it's also possible to make a cyclic acetal, and the way we get that is we use this. When you take a look at this structure, it has, it contains both equivalents of OH, and it's a diol, right? So if I use a diol rather than a regular alcohol, what can happen is that one molecule can deliver both equivalents of the oxygen, and the structure we're going to end up with then has those 2 oxygens still tethered together. We're going to get a cyclic acetal. Mechanism for that formation, exact same mechanism we just saw for the acetal formation, except when that second molecule of the second equivalent of oxygen comes in, it's not a separate molecule, a separate alcohol coming in and attacking. It's going to be an intramolecular attack of the oxygen that's already tethered to the molecule. Okay, so we can also make cyclic acetals, and just like any acetal, reaction of this with H3O plus would regenerate the carbonyl and get rid of that alcohol molecule, in this case a diol molecule. So let's take a look at that reverse process. We call that hydrolysis of acetals, reaction of an acetal with H3O plus. And this is something that regenerates the carbonyl. So if I take an acetal, how do I know this is an acetal? What does it mean to be an acetal? You have one carbon with two separate OR groups attached. When I have this, then I treat it with H3O plus, so that means we have water and we have some strong acids. So you can either see it written as H3O plus, or you might see it as written as H2O, H2SO4, something like that. Okay, when that happens, we take that carbon with the two separate OR groups and we bring it back to being a carbonyl, where both oxygen bonds are going to the same oxygen. Okay, what else do we form here? Well, these two molecules of methanol are going to come back out. And so we're doing the reverse of that acetal formation. We call this hydrolysis. Just a quick question: is it an oxidation? Anytime we've seen a reaction that forms a carbonyl like this before, we've described it as an oxidation. Would this mechanism be described as an oxidation? Why or why not? What do we expect in an oxidation reaction? We expect to increase our number of CO bonds. So how many do we start with? We started with 2 CO bonds, and now we have still 2 CO bonds. No, because we have 2 CO bonds to begin and at the beginning and at the ending. So this is not, we don't use an oxidizing agent, right? We're just using water. This is hydrolysis. This is reaction of water, and we're trading one CO bond for a different CO bond. It's going to be, again, characteristic of reactions that we describe as hydrolysis down the line. So it's good to kind of think of that term. Okay, let's see if we can do the mechanism. Turns out that the mechanism is the exact opposite of the acetal formation. So however many steps our acetal formation was, we're going to have that exact same number of steps for the hydrolysis. And in fact, every structure along the way that we saw in the forward direction, we're going to go through those exact same structures as we move back to the carbonyl. Okay, so we have our acetal. We're treating it with H3O plus. Tell me what, think about what you would do first. How do you get started here? We have acid, right? So anytime we have acid, we're going to protonate first. We always know how to get started. So where can we protonate? Must be one of these oxygens on the acetal. So we could just say HA if you want for H3O plus, that's fine. Remember, this step, though, is reversible. We can protonate, we can deprotonate. We can protonate, deprotonate. But let's see what happens when we protonate one of those methoxy groups. What does that do for us? Where do we go from here? Well, this is a pretty interesting intermediate. It's an interesting intermediate because we have a group with a positive charge, and on that same carbon, we have another group with lone pairs. We have a name for this. It's some kind of charged tetrahedral intermediate. Yes, there it is. This is a CTI. Ding, 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 ding. Bells and whistles going off in our head. Every time we see that structure, what do we know it can do? It can collapse, and that's exactly what's going to happen. So how do we collapse that? It's going to be 2 arrows. We have the one group of the lone pairs forming the pi bond, and that's what's kicking the leaving group off. So these 2 arrows are going to be very useful to us. You might see this mechanism drawn slightly differently in other textbooks, but look what happens when we use the 2 arrows to do that collapse. It brings us to a structure that we recognize. It's a carbonyl. We know what to do with carbonyls. Okay, so here, if you're keeping track of all your ingredients, our leaving group just left, we just kicked out one equivalent of our methanol. And tell me about this oxygen that did the kicking out. This is a now positively charged oxygen. We have a carbonyl with a positive charge. What do we have? We have a great electrophile. We just made a great electrophile. So what is going to happen to that great electrophile? I'm going to look around for a nucleophile. And what nucleophiles do we have? Well, we just formed methanol. Methanol could add back in and go backwards. So remember, every one of these steps is reversible. But what nucleophile do we have the most of? Remember, our solvent is water. We have a huge amount of water here, so water is going to be our nucleophile. So it adds into the carbonyl. Now we have a neutral methoxy up here, and we have water attacking. So what's left with on this oxygen? We still have 2 hydrogens. Any lone pairs? We have 1 lone pair and a positive charge. Very good. Where do we go from here? Now what? Well, if you're looking very carefully, you see that we just made a new CTI, and that's quite true. Now, if this CTI collapsed, who is your leaving group? The water here is your good leaving group. So if this CTI collapsed, where would it bring you? It would go right back to where we started. So again, yes, water can add in, water can get kicked back out. So in this case, collapsing the CTI is going to move us in the forward direction. What will move us in the forward direction? Right? We don't want water to be our leaving group. What do we want to kick out? What do we want to replace? What do we want to? We have 2 methoxy groups. We want to get rid of both of them. So we've already gotten rid of one. What we eventually want to do is get rid of this other one. So what we're going to need to do is make this oxygen the good leaving group, not this oxygen. So how are we going to get there? Let's first deprotonate down here to go back to a neutral intermediate. Okay, and I want you to look closely at this intermediate, see if you could describe it. How would you describe this intermediate? When you have a carbon with a methoxy and an OH on the same carbon, an OR and an OH, we call this a hemiacetal. And of course, we went through the hemiacetal. We created this in the acetal formation mechanism. We have to go through that exact same intermediate in the acetal hydrolysis mechanism. So we're here, and how do we go from here to the carbonyl? We said we wanted to get rid of that methoxy group. So let's protonate up on this oxygen, because that's going to turn that top oxygen into the good leaving group. Okay, I feel that we're moving in the right direction here. It looks like a good leaving group. Now, how does this leaving group leave? Where do we go from here? Now we have a CTI. Ding, 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 ding. We have a CTI that is the one that has a group with lone pairs and a group with a positive charge, that where this is now our leaving group that we want to replace. So we essentially went from one CTI and converted it to another CTI, the one that's going to move us in the right direction. So we deprotonated in one position, reprotonated in the other position. Now we're ready to kick out that methanol. How do we do collapse? How do we collapse the CTI? How many arrows? We're going to use 2 arrows. So the lone pair forms a pi bond. That's what kicks the leaving group out. Here we just kicked off our second equivalent of methanol. And by using those 2 arrows, it brings us to a very recognizable intermediate. It brings us very close to our product, because now we see the carbonyl. We know we have a carbonyl in our product, and we see that we're once again just a proton away. We just have to deprotonate, and we would get to our final product. So let's do that. A minus. Can grab that proton. Kind of work myself into a corner. Make sure you give yourself plenty of room. Nice big blank piece of paper when you go to do these acetal mechanisms or acetal hydrolysis mechanisms. We're getting into the territory of giant mechanisms. And so don't be afraid to kind of snake around up and down and work that way. Don't stop and redraw a structure so that you can go left to right, because every time you redraw a structure, you have a chance for making mistakes and you have a chance for wasting time. Both of those we can't afford to do, like when it's an exam situation. So just go ahead and snake your way down the page, and finally we get to our final product. Also resist the temptation where I now have to flip this over so it looks like the carbonyl up here. No, we're done. We're back at our aldehyde. We kicked out both of our molecules of methanol, and we've completed our hydrolysis of the acetal. So what other nucleophiles can we have to the carbonyl? There's one more to take a look at, and that is a nitrogen nucleophile. And we're going to look at two types right now. We're going to look at either ammonia or a nitrogen with just one carbon group attached. We call those primary amines, so it has the formula RNH2. Okay, and of course the nitrogen is going to be a nucleophile, and we know the carbonyl is an electrophile. This is a reaction that again is typically acid catalyzed. Okay, and if we were to look at the oxygen example, what happened when we had an alcohol? You might think, well, maybe we replace the CO double bond with two nitrogen R groups. Okay, kind of like an acetal, but that's not what happens with nitrogens, because nitrogen can have 3 bonds. And so what happens instead is we simply replace the CO double bond with a CN double bond. And that nitrogen had an R group attached. That R group is still there, and that's the product we get. This is called an imine functional group. When we have a CN double bond, we call that an imine. And what is the second product that's formed in this reaction? What else is formed? We lose these 2 hydrogens and this oxygen. So eventually, somewhere in the course of the mechanism, we're going to be producing water. And this is another case where every step, just like the oxygen, every step along the way is going to be reversible. So the only way we can push it forward for the imine formation is we have to remove to drive the reaction forward. To push the equilibrium in the forward direction and remove the possibility of doing the reverse reaction, we have to remove the water as it's formed. Okay, so just a quick example. And what's interesting about these reactions, it has this same general format, but this group, the one group that's attached to the nitrogen, you can have a wide variety of groups here. It doesn't have to be just a carbon. It can be another nitrogen. It could be an OH. It could be just about anything. But whatever is attached to this NH2 just is along for the ride. So the way we can draw our product is we replace our CO double bond with a CN double bond. And then we know that nitrogen has 3 bonds, and we take a look back to see what was attached to that nitrogen. In this case, it was a methyl group, so that methyl group is still there. We know at some point these hydrogens must be lost because in order to get a neutral product, the nitrogen needs to have just 3 bonds in a lone pair, and so that's why we end up dropping the hydrogens and just carrying along that one alkyl group or whatever group happens to be attached. So let's see if we can do a mechanism for this reaction. Let's assume we have an acid catalyst. And so I think our first step is going to be protonate. Where should we protonate? The carbonyl is going to be the place to start. So we could just say HA for our tosic acid in this case. We can protonate. This is a reversible mechanism. Reversible step. Of course, you can protonate. You could deprotonate. Okay, what does protonation of the carbonyl do for us? It turns our good electrophile into a great electrophile. The presence of that positive charge tells me that it is even more electron deficient, so it's really going to be looking around for a nucleophile. What nucleophile do we have around? Well, the amine is going to be an excellent nucleophile. In fact, the amine is such a good nucleophile, it doesn't even have to have a protonated carbonyl. So you might see some variations in mechanisms when you're looking at amine formation. This can actually be done without the acid catalyst, but it's just kind of nice to show that here. So our nucleophile is going to attack the carbonyl. Again, reversibly so. And this nitrogen now has the methyl. And it still has 2 hydrogens. And what we did was we protonated, and then we attacked, and now we can deprotonate to get to a neutral product. So I can have my A minus come back. And go from here and get to this neutral product. Protonate, attack, deprotonate. Such a common sequence we're going to see for acid catalyzed additions. Okay, well, we're kind of halfway there. We've introduced the nitrogen. We still have this oxygen. Where do we need to go? We need to eventually get rid of this oxygen. Remember, our second product here is water. We're forming water. That oxygen of the carbonyl is going to leave as water. So how do we get that to go? We protonate the oxygen to make it a good leaving group. And again, anytime you're stuck here, you're at a neutral product, neutral intermediate, and you have to think about what to do next because we are in acid conditions. The way to get out of that hole is to protonate something. Okay, we could protonate this nitrogen, but that would move us backwards. We could protonate this oxygen, and that would move us forward. How is that a good thing? What does that do for us, protonating that oxygen? How do I know that can take me forward in my mechanism? Not only did I make this a good leaving group, but I also made something else that's kind of special here. It looks to me like a charged tetrahedral intermediate. Yes, this is another case. Carbonyl chemistry, we're going to see this again and again. A charged tetrahedral intermediate, which means the way I'm going to get rid of that leaving group is I'm going to collapse that CTI. I'm going to use 2 arrows. This lone pair is going to form a pi bond, and that's what's going to kick out water. So here's our example. Here's the point in our mechanism where we lose our water molecule. And our product for this step is going to be the following: nitrogen with a double bond. And of course, that's an N+. We have 1, 2, 3, 4. Nitrogen wants 5. So we have an N+ here. Now, we've seen this part of the mechanism before with oxygen, and at this point when we had the oxygen, this is now when we added in our second equivalent of oxygen, and we ended up with the acetal with 2 OR groups. Okay, but the nitrogen can do something different to stabilize this molecule, and that's because nitrogen can have 3 bonds, wants to have 3 bonds to be stable, and so there's a very easy way for it to get rid of its 4th bond. What can we do here? We can just deprotonate and get rid of that hydrogen, and that's exactly what happens. Our A- comes in and deprotonates, and we're done. So the imine mechanism is significantly shorter than the acetal because we didn't have to add in 2 equivalents of the nucleophile. We just add 1 equivalent, and it ends up replacing both CO bonds with CN bonds, and it can still accommodate this 3rd group that it came in with. Now, another reaction that we can take a look at, moving away from nucleophilic additions to carbonyls, are oxidation reactions. This is where we increase the number of CO bonds while decreasing the number of CH bonds, the number of CH bonds. And so the biggest case where this is going to be relevant is when we're looking at aldehydes, because an aldehyde is the only carbonyl that has a CH bond that can be lost. We can lose this in an oxidation. So if we give a very strong oxidizing agent like Jones conditions, chromic acid conditions, absolutely we can replace this CH bond with a CO bond. Now, how would I finish up this structure to make it look like a recognizable functional group? I would just turn this oxygen into an OH. Okay, so we could take an aldehyde and convert it to a carboxylic acid by oxidation, by chromic acid oxidation like Jones conditions, sodium dichromate and acid. Right, and that's just like we've seen this before. We've seen Jones before if we had a primary alcohol and we use Jones conditions we made the carboxylic acid. So we've kind of seen this reaction before, starting with an alcohol, and we saw that if you partially oxidize it to an aldehyde, you wouldn't be able to stop. It would go all the way to the carboxylic acid. And here we're just seeing an example where if you started with the aldehyde, this could also be subject to oxidation and can go to the carboxylic acid. Okay, if we used our other oxidizing agents, though, like PCC or Swern, remember we used PCC or Swern to make an aldehyde. That means that they must not react with aldehydes. If we wanted to do that, oxidation would be impossible. So we need a strong, harsh oxidizing agent, something like chromic acid. Okay, how about if we had a ketone? If we did Jones or PCC or Swern oxidation conditions, any of these, and we try to do it on a ketone, here's a case where there's no CH to lose, and so we're going to have no reaction with these. The only oxidation we could have would be breaking a carbon-carbon bond. That's going to be much rarer and not going to happen with any of the oxidizing agents we've seen before that would oxidize primary or secondary alcohols. So the very limited options here for oxidizing, and we're just going to start with the aldehyde and do a strong oxidizing agent to make the carboxylic acid. When it comes to reductions of carbonyls, either aldehydes or ketones can undergo reductions. And one possible, remember, a reduction now is going to be a decrease in the number of CO bonds and an increase in the number of CH bonds. So for example, we can go from a ketone or an aldehyde to an alcohol, and that would be an example of a reduction reaction. Okay, how could we do that? Well, there's two methods we could use, two types of reagents that will do this. One possibility would be using a hydride reagent, so something like a nucleophilic hydride, like lithium aluminum hydride, or sodium borohydride would work great here. So that's taking advantage of the fact that this carbon is electrophilic. And so if we had a nucleophilic hydrogen, that would clearly add to the carbonyl and give an alcohol product. In fact, we've already seen that this lesson as one of the examples of the nucleophiles that can attack. So that would be one way to reduce a carbonyl. Another option we have for reducing a carbonyl is a very special kind of catalytic hydrogenation using a special catalyst called Raney nickel. So this is nickel with hydrogen gas adsorbed onto it. And this combination of hydrogen and catalyst, it does a catalytic hydrogenation, but it's one that reduces a carbonyl. We've never seen that before. The only catalytic hydrogenations we've seen before have reduced carbon-carbon pi bonds, either alkenes or alkynes. And so if we use this special catalyst, it will also reduce a carbonyl. And just like we saw before for catalytic hydrogenation, you break the pi bond, you add a hydrogen here, you add a hydrogen here. And so that would also give this alcohol product, right? What's new here is not just the OH, but it's the CH that's critical. Okay, but because it is catalytic hydrogenation, this is also something that would reduce an alkene. So if you have an alkene in the structure and you want to reduce it to the alkane, you could use Raney nickel. But if you wanted to only reduce the carbonyl and not the carbon-carbon double bond, then we would use a hydride reagent instead, which only is going to go after the carbonyl oxygen. Now, another type of a reduction would be to take a ketone or an aldehyde and completely reduce it all the way to an alkane. Okay, when you have a CH2 group, that's called a methylene. And so it's possible to reduce a carbonyl, not only a partial reduction to an alcohol, but it's possible to completely reduce it to a methylene. And again, there's two good options for this reduction reaction. One of them is called the Clemmensen reduction. That's where you use a mercury zinc amalgam and HCl and water. It's called Clemmensen. Another option is a Wolff-Kishner reduction. This is a two-step procedure. We add in NH2NH2. Sometimes we just draw this as N2H4. That molecule is called hydrazine. So first we treat the ketone or aldehyde with hydrazine. Can we predict the product of this first step? That would be an interesting thing. What happens with this first step if you were to take hydrazine and react it with acetone or some other ketone or aldehyde. What did we see as a reaction with a nitrogen, with an amine, and a carbonyl? Well, what's going to happen is we're going to replace the CO double bond with a CN double bond. Remember how I said whatever group is attached to the nitrogen is just along for the ride? Well, that's what we get. We get a CN double bond with a nitrogen attached. These functional groups are called hydrozones. And they have some interesting uses for analysis. So if you react with hydrazine, you get a hydrazone. And what's interesting, one reaction that hydrozones will undergo is when you treat them with base and heat, it will do an elimination reaction that replaces the CN double bond with CHs. Okay, I'm not going to talk about either of these mechanisms, although the Wolff-Kishner has a pretty cool mechanism. You'd be able to do the mechanism for the first part, and the mechanism for the second part is also an interesting one, but that you should be able to follow. But for the most part, these two are usually given as yet another set of reagents in order to do a synthetic transformation. If you wanted to take a carbonyl and reduce it all the way to the alkane, you could use either Clemmensen reduction or Wolff-Kishner reduction. Can you think why chemists have developed these two complementary methods? Why, a lot of times we just give you one possible, one exemplary reagent to use for a given transformation. But why have these two maybe been used so widely? Well, looks like clearly the Wolff-Kishner reduction involves a strong base, and the Clemmensen reduction, this is a redox reaction doing a metal reduction. It uses acid. And so clearly, depending on the rest of your molecule, what other functional groups you have, in certain cases you would prefer an acidic reduction reaction versus a basic reduction reaction. And so that's why you almost always see Wolff-Kishner and Clemmensen being presented in tandem as two complementary methods you can use. Now, one last thing to talk about is the reason that we are looking at acetals. Why are we spending all this time seeing the acetals and looking at the mechanism? How do we make them? How do we take them off? Is because they have a very useful role in organic synthesis. They also have very useful roles in natural products, and we'll see acetals and hemiacetals in a variety of organic structures, especially sugars. Okay, but one other use that they have that's critical in organic synthesis is the use as a protective group. Okay, and so I just want to talk a little bit, now that we know about acetals and how to make them, I want to show an application of those as protective groups. Now, the strategy behind a protective group is, let's imagine we're doing a synthesis of a target molecule, but instead of just having a very, very simple target molecule where there's one functional group, let's say we have multiple functional groups. And what we want to do is we want to do a transformation that involves just one part of the molecule, and we want all the other parts of the molecule, all the other functional groups to not react. One way to achieve this, and the way that's typically done, is we use a protective group that we hide, we put on a protective group and essentially hide that functional group so that we could do the reaction somewhere else in the molecule, and then when we're done, we can take that protective group back off and get the functional group that we wanted. So again, if you imagine a target molecule that you're trying to synthesize that has 50 functional groups on here, what we do is we kind of protect them all, and then we deprotect over here and we do a little manipulation, maybe we reprotect it. And then we deprotect over here and we do a manipulation, we reprotect it. So with the use of protective groups, you can make fantastically complicated functional groups, molecules with a variety of functional groups that might appear that you wouldn't be able to do some of those transformations without protective groups. Okay, and so let's see just kind of how acetals fit in this picture. If you start with a carbonyl, if you have a carbonyl in your structure, we know those are excellent electrophiles. We've seen again and again how nucleophiles can add into them. Okay, well, if you treat it with an alcohol and you make it an acetal, it's no longer an electrophile. This structure has no leaving group. It has no pi bond like the carbonyl did. It has no resonance. It no longer has the acidic hydrogen that we're going to see that ketones and aldehydes have, carbonyl compounds have. Okay, in other words, it is protected. It is no longer, we've taken away that electrophilic nature. And so if we try to react with a nucleophile or a base, if we try to deprotonate it, if we try to do some kind of substitution or addition, it doesn't happen. There's no reaction. So kind of like an ether is a pretty stable functional group and doesn't do a lot of reactions. Acetals are very similar that way. In fact, there's only one reaction that we've seen of acetals, and that was the reaction of an acetal with H3O+. What happened there? It underwent hydrolysis, and it gave us back the carbonyl that we had started with. So in fact, this one reaction that it undergoes is useful to us because the key of having a protective group is not only that you can put it on and temporarily hide the carbonyl, but then you have to be able to take it off as well and get that functional group back. So acetals are really ideal for this situation. Okay, let's see an example where you would need that. Okay, consider the following synthesis. Let's say I wanted to make this target molecule, and the plan that I had for that is I would start with this halide. I'd react with magnesium to make this Grignard, and then I would react with formaldehyde, and that Grignard could attack the carbonyl and make this alcohol after a workup. Okay? Good idea, reasonable idea for handling the reactivity of this carbon, but what's the problem with it? This reaction would never work. The synthesis would never work. And where do I have an error? Well, right here, I have a Grignard, which is a very strong nucleophile. And in the same molecule, I have a carbonyl, which is a great electrophile. In fact, we just said that we utilize the fact that Grignards react with carbonyls. Yet we had a carbonyl right here that we chose to ignore. Okay? Now, you might say, well, oh, it can't happen intramolecularly, because it's not the right distance away. But remember, you never have a single molecule of this Grignard reagent. You have a solution of these Grignard reagents. You have millions of them. So even if they can't react intramolecularly, you certainly would have one molecule attacking the other molecule and doing a Grignard reaction that way. Okay, so what we have in this case, in this plan, the synthetic plan, is we come across some incompatible functional groups. It is impossible to have a Grignard in the presence of a carbonyl without having them react. Okay, so how can I synthesize this molecule? I need to protect my carbonyl. I need a protective group. So what I'm going to do first is I'm going to convert this to an acetal. This is where the diol comes in handy. A lot of times we'll see this being used. Of course, you can use any alcohol you want. But if we use the diol, we would get the cyclic acetal. And now our carbonyl is gone. Our carbonyl is hidden. It's masked. There is no carbonyl any longer. And so now, if I took this structure and added magnesium, I could make the Grignard reaction, make the Grignard reagent. This Grignard is okay. It's possible to make this Grignard. These are now compatible. The Grignard would have no reaction with the acetal. So I hid my carbonyl. Now I can make the Grignard. I can use the Grignard. So I can add in my formaldehyde and my workup and do my Grignard reaction. And then at the very end, to get to my desired target molecule, I need to remove the protective group. I need to get rid of that acetal. And how do I do that? I use water and acid, H3O+. Hydrolysis. So I know how to put an acetal on with an alcohol and acid, and I know how to take it off with water and acid. And now you'll notice this workup for the Grignard was H3O+, and then removing the protective group was H3O+. So sometimes we don't have to draw that twice. Sometimes you can indicate, well, this H3O plus is vigorous enough conditions that it'll both protonate the O minus and it will hydrolyze the acetal. But maybe we can control the pH here to do them stepwise or so on. But sometimes you might see them all in one step, or you might see them separately. So this would be a great way to do a synthesis, have a synthesis be allowed by using a protective group. Now, while we're talking about protective groups as a general strategy, let me also introduce the fact that carbonyls are not the only thing that can be protected. A wide variety of functional groups. There are protective groups that have been developed for each of those functional groups. For example, an alcohol. An alcohol is another functional group that is ubiquitous. We have a lot of these, and we want to be able to hide an alcohol. The most notably, what we need to get rid of on an alcohol is the acidic proton, because that can interact with different reactions. It will be available anytime we have a strong base. And so there are several strategies we can have for this. One that's very commonly used is we take an alcohol and we treat it with trimethyl silyl chloride. This is called TMS chloride for trimethyl silyl chloride. We take this and some base, and what happens is the silicon is going to attach to the oxygen. So we're going to lose this proton, we're going to lose this chloride. So because we are generating HCl, that's why we need the base here, something like pyridine maybe. And what happens is we attach the silicon onto the oxygen. It's kind of like using tosyl chloride to make the tosylate. But when we use the TMS chloride, we get what's known as a silyl ether, and this is another substrate that is very unreactive. Kind of like a regular ether, it's very unreactive. So if we try to, if we no longer have the OH group here, we no longer have that acidic proton, and so this is protected. It's protected as a silyl ether. You could draw this. Usually we don't draw out our protective groups. We usually use abbreviations to represent them. So this is called the TMS group, and so this is called OTMS. And there's a wide variety of silyl ethers we can use. Instead of using a trimethyl, you can replace one of these with a tert-butyl. That's called tert-butyl dimethyl silyl chloride, TBS or TBDMS. Or you could have 3 ethyl groups. That's called TES for triethyl silyl. A really wide variety that have different stabilities and different applications. Okay, but they all have these interesting abbreviations. So when you're looking at a multi-step organic synthesis in the literature, it kind of looks like alphabet soup. You see all these acronyms, all these abbreviations all over the place to represent the protective groups that are being put on and taking off at various points in the synthesis. Now, what's really cool about silyl ethers, and the reason they're so widely used, is they're very stable to a variety of reaction conditions, except when we want to take them off, we need to be able to do that, and the reagent we use for that is tetrabutyl ammonium fluoride. I'm sorry, tetrabutyl ammonium fluoride, which is called TBAF. It's called TBAF for short. So when we're done with our silicon group and we want to take it off, we add in some TBAF, and what happens there is silicon fluoride is something that loves silicon, and it's going to attack the silicon and release the oxygen, something like this. F minus will come in and attack the silicon and cleave that ether and give us back our alcohol. Okay, and how many reactions have we seen up to now that use fluoride as a reagent? Going to be very rare. We're not going to be using that ordinarily, so we're not going to encounter that unless we want to remove a silicon protective group. So this is another great strategy to hide an alcohol. We can protect as a TMS ether, and then we can remove it by using TBAF. So let's see an example where we might need to use a protective group. In this transformation, we have 2 things we need to accomplish. We have a carbonyl that we're going to convert to an alcohol. Have we ever seen that transformation. Looks like a reduction, right? We need to reduce the carbonyl at some point as part of our transformation. And we also have this carbon as a bromine, and now it has a carbon change, so that's a new carbon-carbon bond that we also need to accomplish as part of our synthesis. So we need to do two things. We need to reduce the carbonyl and form a new carbon-carbon bond, and we can do either one first. Doesn't really matter. So let's say we wanted to do this disconnection. Okay, if we want to do this disconnection first, we look at these two carbons and we say we want to make this, one of these has to be a nucleophile, one of them has to be an electrophile. So because this is the carbon with that now has an OH, what does that look like? I think this was my electrophile as a carbonyl. And how about the other carbon? How do we make this a nucleophile? Remember, we have an alcohol product here. How do we make an alcohol? What two ingredients do we need? We want a ketone plus a Grignard. Ketone plus a Grignard gives an alcohol. So this is my carbonyl, and the other carbon we're going to make a Grignard. So if I had this Grignard and this ketone, well, it's not really a ketone, is it? It's two carbons, so it's just this aldehyde. So let's say it's a ketone in quotes, and in this case it's an aldehyde plus a Grignard. If I had this aldehyde and this Grignard, that could make my product. Okay, so that's a good plan. The problem is that this alcohol, that Grignard, is impossible to make. We have another example of incompatible groups. It is incompatible because this Grignard is a very strong base, extremely strong base, just like we use butyllithium as a strong base, a Grignard would be a really strong base, and of course an alcohol is an acid, is acidic. And so if you have a Grignard in the presence of an alcohol, it simply protonates the Grignard, you quench your Grignard, the reaction's over. There's no way you could use that. Okay, so what we can do is we can protect. We have to protect our alcohol in order to do this Grignard. Okay, so we kind of have a plan here. Let's think about getting to this alcohol first. Okay, how did we get this alcohol? How do we go from a ketone to an alcohol? Looks like we've lost a CO bond. It's a reduction reaction, a reducing agent. What do we use? Something like lithium aluminum hydride or sodium borohydride. We could do sodium borohydride and some kind of protic solvent like methanol or water, ethanol. We can do that reduction reaction, no problem. And then instead of making the Grignard, we have to first protect the alcohol, and the way that we protect the alcohol is we're going to protect it as a trimethyl ether, or any of the silyl ethers, but TMS is kind of our most simplest one we can use, the most common. So we can make the TMS ether. How do you make the TMS ether? You use TMS chloride. You put a leaving group on that silicon, and that's what gets replaced by the oxygen. Again, some kind of base like pyridine. We can use here TMS chloride, pyridine, would be a way of making the TMS ether. Okay, the reason I wanted to do that is because I wanted to make the Grignard here, and I couldn't make the Grignard in the presence of an alcohol. Now I no longer have an alcohol, it's protected, so now I can add in my magnesium, and that has no effect on the TMS ether. This is protected. It's not acidic, and so this is an okay Grignard. There's no problem. Those are now compatible functional groups. Okay, what did I want to do with that Grignard? I wanted to react with acetaldehyde. So I can bring in acetaldehyde. Step 1. Step 2, H3O plus to work up my Grignard. Kind of running out of a little room here. And that forms the new carbon-carbon bond. So we've done the reduction. We form the new carbon-carbon bond. We're very close to our final target molecule. All we have to do is remove the protective group that we put on, so we're temporarily hiding a functional group while we'll do reactions somewhere else in the molecule, and then we want to be able to take that protective group back off. So how do we get rid of a TMS group? We use TBAF, tetrabutyl ammonium fluoride, to do TBAF. Okay, so this is one approach to the synthesis where we do our reduction first and then we do our Grignard. Let's see if we could do the other order and see what that synthesis might look like. Okay, so let's say we wanted to do as our last thing, we wanted to do the reduction last, which means we undo the reduction first. And then we could say, okay, now I want to do the disconnection of the alcohol, which means I go back to my ketone and my Grignard. So once again, this guy was my carbonyl. That was my electrophile, who is now an OH. This was my nucleophile as a Grignard. Ketone plus a Grignard gives an alcohol. So I would need this Grignard plus the same acetaldehyde electrophile, and what do I find in this case? I have another example where I want to make a Grignard, and now I have a carbonyl. That's still no good. I can't have a carbonyl here either. This must be protected. I must protect this carbonyl because I can't have a Grignard in the presence of a carbonyl. So another way to do this problem would be to first protect the carbonyl. How do we protect the carbonyl? We do so as an acetal. So again, this diol is very commonly used, but you could just use a methanol or ethanol or any other alcohol you want. But it's just kind of convenient to draw that cyclic acetal. Now that I have my protective group on there, now I can make my Grignard with no problems, no incompatibilities. Right? This is okay. This is perfectly fine to make. This is the protected version of the Grignard that I needed. And the reason I wanted this Grignard was I wanted to react with acetaldehyde. So now I could say step 1, put in my aldehyde. Step 2, H3O+. Now I've formed my new carbon-carbon bond. And then as usual, I want to get rid of my protective group after I've done the reaction and I've gotten rid of that incompatible part. Now I can remove my protective group. How do I get rid of an acetal? How do I get rid of an acetal? I want to go from the acetal back to the CO double bond, back to the carbonyl. That's simply hydrolysis. Remember, hydrolysis is the only reaction that we have for an acetal that is going to do strongly acidic conditions in the presence of a nucleophile like water is going to give me back my carbonyl. And what did I want to do with that carbonyl? Now I could react it with lithium aluminum hydride or sodium borohydride and H3O+. Okay, now you might say, well, I have hydride here. Can't that react with the alcohol? Actually, it can, but this is a case where LEH is pretty cheap. You could just use an excess. It's okay if you deprotonate over here. That won't stop the reaction with the carbonyl, and then the aqueous workup can protonate both of them. Or maybe you could use sodium borohydride, NaBH4, and methanol, let's say, a weaker hydride reagent, and then that would be compatible with the alcohol. So either one of these would work well. But the point is, in this reaction, because we want to do a Grignard and we have another functional group somewhere else in the molecule, if that functional group is a carbonyl or it is an alcohol, we have to protect either one of those. We have to protect them so that we can do the Grignard reaction and then deprotect them when that reaction is done. Okay, let's look at just a few more transforms, a few more examples now that we're finished looking at reactions of carbonyl compounds. How about if we wanted to do the following transformation? We see that we have a 3-carbon chain here. Let's find those 3 carbons. Looks like they're right here, 1, 2, 3. So what's nice about that is it tells us what disconnection we need to do. Okay, so these are the two carbons that we want to bring together. As usual, we have to ask what was our nucleophile, what was our electrophile. We're asking what starting materials do I need? What starting materials do I need? We have an alcohol that we're disconnecting. We've seen this again and again. And so when we do that, the carbon that is now a single bond OH used to be a C double bond oxygen, used to be a carbonyl. So this was my electrophile as a carbonyl. So how do we make this carbon, an ordinary carbon, a nucleophile? We add a metal. We make it a Grignard. So the alcohol disconnection brings us back to a ketone plus a Grignard. Our Grignard is this guy, isopropyl magnesium bromide, for example. And our carbonyl is not a ketone, actually. It's an aldehyde. It's another example where we're using acetaldehyde. You could leave the structure like this, but we usually draw on that hydrogen there for the aldehyde. So what's great about a retrosynthesis is you can check your work. You can say, you know, if I had this nucleophile, if I had this Grignard, and I had this electrophile, this aldehyde, would they come together to make my target molecule? They would. You can check that mechanism. You can double check, and now you know you have a good plan. So now all we have to do is figure out how to make isopropyl magnesium bromide when we're starting with isopropyl bromide, and that isn't too hard to imagine. All we need to do is throw in magnesium. And once we have the Grignard, we can add in our electrophile, followed by H3O plus workup, and we have done our transformation. Okay, and let's see another one. Now we have an interesting example. We start with a carbonyl, and we need to go, and we want to go to an alkene. So we can think about how do we make an alkene. Well, and the other thing we want to keep in mind is that we started with 3 carbons. We still have just 3 carbons. So we did see a Wittig reaction as a way to make an alkene this chapter, but the remember, a Wittig reaction adds carbons to the carbonyl carbons that are already there. So because we haven't added any new carbons, we wouldn't want to be using a carbon nucleophile in this case. This is simply a functional group interconversion, a functional group interconversion, because we're not changing our carbon structure at all. So then we think about, we have an alkene. What are some ways that we can make an alkene? What starting materials do I need? What functional groups have I seen where upon reaction they give an alkene product? And we also want to kind of keep in mind that it came from something that we can make from a carbonyl, right? So we're working forwards a little, we're working backwards a little, we're trying to find that key intermediate structure that we can both get to and go from. And one reaction that's reasonable here is, how about dehydration of an alcohol? If I had an alcohol, right, I need to do some kind of elimination to form a double bond. So I can either have an alkyl halide and do an E2, or I can have an alcohol and do an E1. And what's great about an alcohol is I know that that's something I can create from the carbonyl, and then I know that I can go to the alkene. Okay, that would be great. So how do I go from a carbonyl to an alcohol? That looks like a reduction reaction. So this is lithium aluminum hydride, for example. 2 steps, H3O plus. So that gives us an alcohol. Remember, we also learned about Raney nickel. Raney nickel NiH2 also does this reduction of a carbonyl to an alcohol. That would be fine too. And then once we have this alcohol, we want to dehydrate, we want to lose water. What conditions will remove water from an alcohol? We need a strong concentrated acid, something like H2SO4, and heat does a dehydration. So this would be a good way to do this transformation. Again, 2 simple reactions we've seen before, but using them in combination, now we see how to go from a ketone to an alkene. How about the next one? We want to go from, what functional group do we have here? We have an acetal, and we want to go to an alkane. Now, the acetal is closely related to what functional group? It's, where do you get an acetal from? You get it from a carbonyl. And what's the only place we can go from an acetal? We can go to a carbonyl. That's the only place we can go we can either, we start with a carbonyl to make an acetal, and from an acetal, we can go back to the carbonyl. Okay, so this must involve going back to the carbonyl. And now, do we know how to go from a carbonyl to an alkane? That looks like some kind of reduction, right? So, so this second part is a reduction. And this first part, what does it look like here? Is this an oxidation to get to a carbonyl here? No, remember, we started with 2 CO bonds. We still have 2 CO bonds. It's not an oxidation. This is simply hydrolysis. Acetals can be hydrolyzed to give the carbonyl. So this first step is just H3O plus. Gives that big long mechanism we saw for hydrolysis of an acetal. And the second step, how do we go from an carbonyl all the way down to an alkane? In other words, we want to have 2 hydrogens here. We saw 2 methods for this. We saw the Clemmensen reduction and we saw the Wolff-Kishner reduction. And either one is fine. So Wolff-Kishner is N2H4 and NaOH and heat. So again, get some flashcards together to become familiarized with these reagents. That's the Wolff-Kishner. The Clemmensen is zinc and mercury amalgam and HCl. Those kinds of reaction conditions will be the acidic redox reaction. Okay, and one last example. Let's turn the table around and ask what starting material did I need to get to this product. Okay, and if we're used to doing transform type problems and if we're good at doing those planning, this is a piece of cake because that's every time we do a retrosynthesis, we're asking what starting materials did I start with. Okay, and the key is we're given that this is our final product, and what was the reagent that we reacted it with? We had a phenyl group plus a CH2. We had a 1 carbon plus the phenyl group. Here's our phenyl group. Here's our CH2. This is the new carbon group that's been added. Okay, furthermore, we have a benzyl magnesium bromide. We have a Grignard reagent. What's the reactivity of a Grignard reagent? This is a nucleophile. So we already know that carbon 1 here was our nucleophile. So even if we couldn't see it for ourselves, we know what's required. We need a 2-carbon electrophile. This was an electrophile. What's it going to look like? What electrophile can we have that after a Grignard adds to it, we're going to have an OH here? It's going to be a carbonyl. It's going to be a carbonyl. So what we need is a 2-carbon. We could draw it upside down if you want so that you can kind of track along. A 2-carbon carbonyl, this aldehyde. Once again, here's another example of acetaldehyde. And then we could treat it as a predict the product, see if we got it right. If we had this Grignard, it would attack the carbonyl, break the pi bond, and after workup, we would get this phenyl plus these 3 carbons, and that would be our final product. Okay, so a lot of interesting things we can do with carbonyls, ketones, and aldehydes. We could do some oxidations and reduction reactions, but the vast majority of our reactions are going to be reacting the carbonyl as an electrophile, and so we add a variety of nucleophiles. We could add hydride, we could add Grignard, we could add the Wittig nucleophiles, and then when we get to the alcohols and amines, we get some of these reversible reactions where we form acetals and we form imines. Okay, and of course, the importance of acetals not only extends to natural products such as sugars, we'll see that down the road, but also they can be used they become very useful in organic synthesis as protective groups. So thanks for joining me, and I look forward to seeing you again soon.